Okay, you got that? Yeah? Now, the next one is how much work is done. So we have a formula for work. It's, what's it, a half K, or is it K squared? It's a half K squared X squared. You know what, the formula of the book is right here. Let's just check.
Hooke's law?
No, it's not K squared. Yeah, no, it's this guy. Work is force by distance.
Okay.
But Hooke said force is Kx. So this is Kx squared. Now the problem is though, do we know the K? Do we know the K? We don't. We don't. So if you remember, there's another way to do this one, but I think it might be good if we just draw the picture here, okay? So what you have is you have this, and you have this here, and its mass is 5 times 10 to the minus 3 kilograms, and you stretch it down 20 centimeters using a force of 1.5. So I think what's going to happen is if you pull it down with 1.5 newtons, okay, you can keep pulling it until the force up will cancel the 1.5. Do you know what I mean? Like if you can pull with 1.5, you can pull it so far as the force the other way is less than 1.5. And then you have to stop when it pulls back with 1.5. So I think if we use the formula, force up equals force down. So up is Kx and down is weight plus 1.5.
Yeah.
So K we don't know, X we do know, weight we do know, and that's 1.5. So then K is 5 times 10 to the minus 3 times 9.81 plus 1.5 over 0.2.
It's 7.75.
7.75. K is 7.75 newtons per meter. Yeah? So now we can find the answer. What is the work? It's a half Kx squared. So that's 7.75 over 2 times 0.2 squared.
It's half?
No. Sorry, it's not. Thank you. Wait. Yes. Yes, it is a half. I gave you the wrong formula earlier. So the reason for the half is, remember it was because of this graph. You have here, what was it? The area. Is this F or X? Yeah. But I forget what's here. Is it X or F? I forget. F? Yeah, F.
X.
Like this? Oh, it's the other way, okay. You're right, Ben. It's like this. So the area is a half Kx squared. Yeah. Yeah.
0.155.
Point, point
155.
55 joules. Yeah? Okay, part 2. If the energy transfer to the initial kinetic is 80% efficient, how much initial kinetic energy does the rubber band have? So, if you look here, can I scroll down?
Because
What's wrong?
the answer is different.
Is it? What's the answer?
Is that right?
We can have a look. Ah, they're wrong.
They're wrong?
They're wrong. Sorry, what was their answer?
0.3. They use the work FX.
No, that's not right. That's wrong. That's very wrong. The reason it's wrong is because if you pull this down with 1.5 newtons, okay, at the beginning, when it's, slack, I know you're pulling with 1.5, but it's not stretched. There's no, how can I put this? Okay, it's like this. No, I apologize. I'm so sorry. I'm wrong. And the reason is, if you can look here, do you see this word here, average? That changes the meaning. Stupid English.
So difficult.
Yeah. The reason is, do you see here, look, this formula here, this works if you use a constant force, like you pull at the same force. However, they used an average force, which means at the beginning the force is small and at the end the force is large, and the average is 1.5. So you can, I'm so sorry, you can actually use this simpler formula. I'm so sorry. Work is force times distance. So that's, I made more work for you. That's 0.2 times 1.5, 0.3 joules. Would you say that as the answer?
Yeah.
Yeah, so that was easier.
That's normally section B1, I think.
Yeah, you're right, Gav. I should have questioned myself. Do you know, it's really is the English, and I'm very sorry. It's because I didn't see the word. The word average, I didn't fully think about.
It's only one function.
Yeah.
I started worrying now, because you even have the
Yeah, sure.
English mistake.
Yes, absolutely.
We can't get
Yeah, absolutely.
God.
The problem is the person who now writes the exam uses a lot of English.
So this hook law.
It's not hook.
Don't need it.
It's work.
Don't need it.
Fx. Okay. Fx.
Force by distance. Or FD if you want. Just for work.
Which formula?
Or FS. I don't know which formula you wrote it down. Just for work. Force by distance.
Oh yeah.
Yeah.
And P equal
Yeah.
W over T.
Yeah, exactly. Okay. Continue. So what happened? Yeah.
Which form is IOD?
Huh?
Long space D?
Huh? Say again?
I don't know if there's and it's not related
Yeah.
with this question. There's any formula like force or something equal LD. Is it? Is there have this formula?
LD?
Allowance or something? I don't know.
I don't know what you're talking about. We'll continue, okay? So what they say is you pull this down and you did some work of, what did we say? 0.3 joules of work. Yeah? That's how much work you did. And then what happens is not all of this energy, but 80% of it will become kinetic energy when it goes back up. But not all of it. They just say, how much? 80%. So they're a little bit wrong. Initial kinetic energy. The kinetic energy at the beginning is 0, so I don't think that's quite what they meant. I think they just meant kinetic energy. So I think it's just 80% of 0.3. So they say that this turns into kinetic energy, 80% of it. So how much kinetic energy do we have?
0.24.
0.24. Is that right?
Sure.
Yeah. Okay, and now they ask you for what's the speed. Well, how do you get that? A half
mv squared.
mv squared, yeah. That should equal 0.24. So that means mv squared should equal 0.48. So that means v should be square root 0.48 over 5 times 10 to the minus 3. And that's our v.
Nine point 8 0.
0?
9.8 0.
Is that okay? Part 4 already. Ben, is that okay? Is that yes or no? Okay.
Yes, yes.
Open the answer.
Okay. Part 4 now is here. Here's the rubber band, and it gets shot up in the air with a speed of 9.8 meters per second. And the question is, what's the maximum height? So you know how to do this. You say the kinetic energy here equals potential energy here.
MGH?
Yeah. So mgh equals a half mv squared. mgh equals...
9.8?
no, I'll do it like this, 0.24.
Oh, there's no.
Easier. Oh, I left my bike outside. Whatever. Yeah. H equals 0.24 over mg.
We did MG before.
The weight, yeah. What is it?
0.005 mod 9.1.
Now wait, before you continue, there's a small problem I have. Again, this is the English not being so clear.
Where?
Yeah, well, he says, what's the maximum height? Now, I don't understand if he means, because he's not clear, if you have like a rubber band and you stretch it, does he mean you let go and it moves up? Or you pull it down but you still have it tied and it goes like this? Do you know what I mean? Do you understand? So I don't know if he meant like you pull it down and then you let go and it shoots up in the air.
Or you still
Or if you're still holding it, yeah. Now you see, the way I did it is if it goes up in the air. Now I think I'm right because the question, you can see, is only 2 marks. Whereas I feel if it was the other way, it should be 4 marks. But we'll check the answer in a minute.
So there's 0.24 4.1 by 0.
Okay, that's.
Sure, brothers.
Are we right or are we wrong?
Yeah.
C.
Yeah.
We're right?
Yeah, 4.9. We're right.
Okay, so
It's too complicated.
this one's not easy, but I think. Yeah, okay. Continuing. The 20% missing energy went towards heat. What is the change in temperature? Okay, so that's just mc delta theta equals 0.06 joules, is that right? Is that right? 0.06? Because they're saying that, remember we said it's 80% efficient, so the 0.06 went into becoming heat.
20%?
Yeah, 20%, yeah. Is that okay, Gal? Or are you confused? It's okay or not?
So 0.24 multiplied 20%?
No. Remember that 0.24 is 80%. The 0.24 is 80%.
Okay, so
Yeah. What happened, it was 0.3 became 0.24 kinetic energy and 0.06 heat. That's what happened. Yeah. So here we got delta theta equals this over this times 1250.
Yeah.
2 marks. Yeah. What's this?
Uh, 9.6 and times 10 rho minus 3. Minus 3.
What did you call this?
power.
No, I wanted him to say it. Power. 10 power minus 3. Okay. Celsius. And now the last part, your favourite question,
Celsius?
or Kelvin, it's the same.
Oh.
Oh, it's K.
Yeah, it doesn't matter, it's the same. It's the same. Yeah?
Oh, okay.
That's the same. Because this is a delta theta, it's a change.
Oh, okay.
Yeah.
Yeah.
I'm sometimes right, Ben. I'm not always right, I'm sometimes right. Okay. You don't like the last one, do you?
No, 6 mark.
Look, we'll just take it bit by bit. A student wants to investigate Young's modulus. Right, so step 1, before we start, let's just remind ourselves, what is the formula for Young's modulus?
Yeah, modulus.
Stress
Stress
over
strings.
strain. And what's stress?
Um,
Force over...
Area.
No. Extension. Oh, sorry. I lie. Area. Sorry, Ben. And strain is extension over length.
Yeah.
Yeah? Okay. Now let's start.
Yeah.
They have an elastic band and they want to measure Young's modulus. So the question is, describe the measurements, the instruments, and how to use your results to calculate Young's modulus. So let's just do first things first. What do they need as measurements? What will they need to measure? So if they have an elastic band, what will they need to measure? Well, first the natural length. That's the first thing. Okay? What else will they need to measure?
The thick.
The thickness, yeah, which is the diameter. How thick it is. The thickness, yeah. What else might they need to measure?
Weight.
Yes, they could. They could. But usually what happens, Gao, is you hang on some weights and it says the value on the weight, you know. So what else would they need? I think, of course, they would need to measure the extension. How do you spell extension? I'm so tired. Extension. T again? S-I-N? Extension. Oh yeah, extension. Extension. Okay. Okay, what else might we need to measure? I don't think we need to measure anything else, do we? Yeah? Now, next question, next part. What instruments?
We.
Instruments next. So what things? No, don't look at your phone. Don't look at your, tell me what things, the instruments, what you would need. How do you measure length? What could you use to measure the length here?
Meter.
Yeah, a meter ruler or a meter stick, yeah. How do you measure the thickness? Yeah, I don't know what it's called. I think it's called capillars, I think. Can't remember right now. For measuring how thick it is. You can check in a minute. And you'll also need marked weights. You know, where it says the weight on it. Yeah? So what do you do? What are the steps here? So the steps would be measure the extension and thickness for different hanging weights. So what I mean is you hang one weight, you measure the extension. You hang another weight, you measure the extension. And then you plot, you could plot, this is stress, and this is strain. Plot strain versus stress. And then 1 over the slope is equal to Young's modulus. I know it's a lot, but it's 6 marks, you know. Now wait, you mean, what did they say in the marking scheme? So what do they have there?
The major thickness is 1 mark. Calipers.
Okay, I spelled it wrong.
Calipers.
Calipers. For goodness sake. How do you spell that?
Calipers.
Hey, that's what I had. No. C-A...
L-I.
L-I.
L-I-P.
Okay, I had my L and my P the wrong way.
P-E-R.
Okay, it should be C-A-L-I-P.
E-R-S.
E-R-S.
That's 1 mark.
Okay, so that's 1 mark. Next.
What is width?
Huh?
Width. W-I-D-T-H.
Width means thickness.
Okay. That's 1 mark.
Okay, so here, 1 mark for saying diameter. Okay.
And length is 1 mark. Ruler is 1 mark.
Great, great.
Extended length is 1 mark.
Great.
And what? Use thickness and width to find area is 1 mark.
Find area?
That's it.
Okay, that's different. So that means this here is 1 mark that we're using the graph. I use the graph to get it.
Okay.
That's it, that's 6 marks, isn't it?
1, 2, 3, 4, 5, 6. But I still have one. Describe use the formula. Yeah, much the formula.
Yeah, so there. 1 mark there. That's a lot, I know. Tough. So maybe you don't want to do that one. Maybe we could look at number 2 now.
I have a picture of it. I don't want to write down.
Continue. Number 2. Okay. A car engine is kept from overheating by water. The water must flow. The water enters at 100, leaves at 40. Okay, so what you have here is you have some water that comes in at 100. I'm sorry, no. What you have is, you have the engine here. Oh my goodness, I can't draw today. You have the engine. Well, they don't call it an engine, they call it a radiator. Water enters the coolant radiator at 100 and leaves at 40. Okay, so what happens is hot water goes in and then cold water comes out. And per second is equal to 2 kilograms. Okay? So what happens is the radiator, can you see? It takes energy. It takes energy. And the question is, how much energy does it take per second? Okay. So that's just using delta Q equals MC delta theta, which is equal to 2, 4180, 60. That's okay. Okay? Yeah? Question?
Per second?
Oh yeah, it's how much is lost per second, so we'll just write here per second, yeah.
Oh, every second.
Yeah. Oh yeah, so it also says, I see there, give your unit the simplest unit. So joules per second, what's the simplest unit for that? Joules per second, Ben knows it? Joules per second?
What? What's the call in English?
What?
What?
It's the same as Chinese, I'm sure.
We say what?
Close enough.
Okay.
Okay.
Yeah? Once the engine is switched off, the cap of the radiator is removed and 200 grams of water is allowed to evaporate. So that means here 200 grams comes out. Taking the energy from the remaining water. If 8 grams of water remains in the radiator system and the latent heat is that, by how many degrees will the remaining water cool down? So what they say here, you have something like this, and there's 8 kilograms of water here, and there's some steam that comes off here, 200 grams, 100 Celsius. And the energy that this got, it took it from the water. So what will happen is this water will be a little colder because the steam came off, And the question is, what is that temperature? Now, what is the temperature of this water? It is it 100 or is it 40?
Once the energy is switched off.
I think it's 100, isn't it? Is it? It's not clear, but I think it must be 100.
Taking from the remaining water.
No.
Remaining water maybe is 100 something.
No, it's 100. Because the radiator inside the car, it cools the water down. If you turn the car off, then the radiator is turned off. It means when the water comes in at 100, it still leaves at 100. There's no cooling anymore. It's like you turn your fridge off. I think. Well, look, I'll see if I get the right. Switched off.
What does mean switch off?
Turned off.
Just close.
Turn the car off. No power. It's off.
Okay, so
No cooling.
so only steam.
So it's here. No, Ben, look here. If you turn this off, it means this still is 100.
Oh yeah.
So I think I should make this 100. Yeah. So look, ml
Yeah.
equals mc delta theta. This m is 0.2, and the L is 334 kilo.
It is steam.
Steam. Yeah.
226.
Huh? John said 334. It says it's 334, no?
334.
But I think it's
So
just
give us in the question.
because it's ice become water.
Ah, you're right, Ben. They used the wrong number in the question. You're right, Ben. Here. He used this number for vaporization, but he made a mistake. It should be this number. But if we're in the exam, we must use, even though it's his mistake, we must use the given number. Yeah. Very good, Ben. Well spotted. Equals 84180 delta theta. And I want the delta theta. Okay, what's this, so? What's that, please?
Why we direct use delta theta.
Yeah.
Equals ml.
Yeah, so what's happening is the energy to turn this into steam was taken from the water. So it's like this. You have water, and then a little bit of it leaves. So the energy gained here will equal the energy lost here. No?
So why we don't use this?
Huh? Oh, that's delta Q.
Delta Q.
This is delta theta.
Oh,
Yeah.
it looks like.
I know, yeah. What's this go? Do you have this?
1.98. So
No, just this? So that's actually 2 if we were to round it. So lost 2 Celsius or 2 Kelvin.
Yeah.
Yeah?
you don't have to. Oh, they only ask the delta theta.
They only ask the delta, yeah, don't they? Do they?
Cool down due to I think.
Yeah.
ML is
Latent heat, yeah. Okay. Oh, sorry.
Yeah.
Celsius.
Yeah? So, water can be used to cool hot metals. The mass of the metal is 250 kilograms. And you need to take the temperature from 300 to 150. And the heat capacity is 450 joules per kilogram Kelvin. How much water would you need to cool it down? You can turn it into steam. So look, what happens is you have water here, and this water is at temperature of 30, and you throw this water onto the wall, and the wall is supposed to go from 300 to 150, and then it comes off as steam. And the question is, how much water do you need? Okay, so let's see. The energy gained by the water will equal the energy lost by the wall. So what happens to the water? It's mc delta theta plus m, the wrong L, because it gets hot and it becomes steam. That should equal mc delta theta. Okay, so m is 250 times 450 times 150 over 4180 times 70 plus 334000.
Should we add the multiply 334?
Yeah, because it turns into steam. They say it in the question. Look.
Oh, so the first part is water, the second part is steam.
Yeah. Okay. Water at 30, which turns completely into steam at 100.
Okay.
Yeah. So what's this answer? Hey, this is okay for 6 marks.
Oh, yeah.
That's 26.9.
Continue. Okay, part C. You're told that there's 18 grams in a mole of water. How many moles are there in 1 kilogram? So the number of moles will equal 1000 divided by 18. What's that? 500 over 9. Something. Help me out here. What's this, please? You do this in chemistry, don't you? Molar.
Yeah.
So what is 1 solvent?
It says you have 1 kilogram.
1 kilogram. Yes.
I'm divided MR.
Yeah. So what is this? About 455, is it?
500 divided 9. 55.6.
0.6 moles. Okay, that's easy, isn't it? Right? 2. What is the volume? So you have the formula PV equals nRT. Did you do this with Lorraine?
Yeah.
Yeah. So V is nRT over P, which is 55.6 times 8.31 times 573 over P, which is 100,000.
Four, two, three, four. This is 2.64. 65.
Yeah. Okay. 3.
Discuss.
Yeah, so it's the same again, except they changed the pressure and the temperature. So now it's 5.56 times 8.31 times 773 over 300,000. That's all.
5.56.
Sounds.
No. Why is 5.56? No, 50.
Oh, it's not. Sorry, that's my mistake. It's of course still
50.
55.6. Yeah. So
1.19.
what? What is it?
1.19.
1.19. Oh yeah, it's compressed. Ah, okay.
So sorry, and to
Yeah, same.
only the temperature and pressure.
Change, yeah.
Only this.
Yeah.
Okay.
That was okay, wasn't it? Alright. Now, this next one here. A potential A potential divider circuit can be used to provide an input for control electronics, e.g. as a light sensor. A light-dependent resistor has a resistance which decreases as light levels. Okay, so look, before I do anything, let me just draw the potential divider. So do you remember it was like this? You have your switch, you have a resistor here, and you have a resistor here. Yeah? But, and then you have a voltage here, and then one of these resistors you can change, which is this one. You can change. Now the only thing that's different, they ask you to draw a potential divider, but instead of using a variable resistor, they ask you to use what's called a, how do I draw this? A light-dependent resistor, which means the resistance changes if there's different light on it. And it's called an LDR. Now, you know these are like what's in the street lights. You know? So, they say, draw this, what do you need? You need a battery? Is that a battery?
No.
No, it's a cell. So there's a battery. Okay, what else do we need? Battery, resistor, LDR, with a voltmeter. So I'll put my voltmeter here. So that's a voltmeter, that's my resistor. or there. And look, there's a switch, which I don't even need.
We're not putting the LDR.
You could, yeah.
Is the same? Serious.
Do they say where? Do you know, because, oh, wait. Yeah, thanks, go. They say, listen, put the voltmeter somewhere so that the voltage increases as the light level increases. So what happens is, more light means more voltage. So you could have your voltmeter here, or you could have your voltmeter here. Alright? We'll call that V1 and that V2. V1 plus V2, that should equal E. If there's more light here, it means more resistance. More resistance means this goes up. But these two should make this. So it means this one goes down.
So the increase.
So if they do say put it where it should increase, so I should put it here. Okay? So that's 4 marks. So what does the marking scheme say?
Question 3. Voltage, battery, resistor, LDR in series.
Hang on, battery, resistor, LDR
in series.
in series.
LDR symbol correct, and voltmeter in parallel with the resistor.
LDR resistor or this resistor?
They just say resistor. Maybe the right one?
I might be mistaken. Can you check here on Google? LDR, I forget if the resistance is increase if the light increase, or maybe it's the other way around. Light increase, resistance decrease. I don't remember.
Resistor.
Yeah, which is it?
Yeah, you're right.
Are you sure?
Because nobody opened the line in some.
Gail's going to check for us.
LDR. Why does the resistance of LDR change and faster?
Let's see, what's it say? No, it's the opposite. When light decreases, resistance increases. So when light increases, resistance decreases, so it means I should put my voltmeter on this one here. Yeah, and can you type in what the symbol for LDR is in Google Images?
LDR is light?
Yeah.
Or resistor? Oh.
Light dependent resistor. It takes the light and changes it into resistance.
So.
Yeah, that's what I drew. Well, put little lines here. Yeah.
It's like morning, looks like. The old morning channel. Just look like the coin.
Where is the resistor change?
There's a resistor here.
But it cannot be changed.
You're right, this one's fixed. This one can change
The light.
by different light.
But you mean the light has a resistor?
The light affects the resistance, yeah. So more light means less resistance.
Okay.
Yeah. Now, I don't like that he did this because this is new. This isn't in any of the other exams. You know, so whoever wrote this exam, I don't think it was fair that he put this in the question because it's kind of a new thing.
So how about this times exam? Anything new? Like anything we didn't learn
I
before?
think, no, it's okay. It's okay.
How about language?
Oh, I
It's the
don't know
same
about your.
as-
I don't know about your language. We'll talk about language later. Okay.
So this light, it doesn't the sunlight.
Could be sunlight, light in the room, any light.
This light.
Oh, this light.
Yeah.
Oh yeah, it could be sunlight.
No. I mean, the sunlight. You mean the sunlight increase, the resistor is
Decrease.
decrease.
Yeah. Is that okay?
Where's the room tomorrow? Here?
I don't know. I have to check. No, let's continue with this, okay? Part 2. If the resistance of your resistors increase, but everything else remains the same, state and explain what will happen to the voltage measured by the voltmeter. Now, I think they mean if you change this resistor. Yeah? So, let me just call this here, you remember your formula, V out, yeah, equals over R1 plus R2 times V in, and this one is like R1, and this one is like R2, and on the top is R2.
R2.
Yeah. So they want to know what happens if you change R2. If R2 is increased, then V out, what will happen if R2 is bigger?
The way out is bigger.
Is it?
Uh-huh.
If R2 increases, what will happen? I think
I suppose. I don't
it's
know.
not clear because it depends on the numbers here. So let's just take an example. Let's just say we have 1 over 1 plus 1. That's equal to a half. And then we increase this to 2. So that's 2 over 1 plus 2. That's a 2 over 3. And then 3 over 1 plus 3. That's 3 over 4. So it looks like it increases. Yeah, so we'll say if R2 increases, then V out will increase. And if R2 decreases, then, of course, V out will decrease. That can't be right. 3 marks. Is that right?
Voltage increases.
Yeah,
Either total resistance increases.
yeah.
Current through LDR decreases.
Yeah. But
as R is constant, V across LDR decreases. Or potential divider arguments.
no, that's what we did. Potential. This is potential divider argument here. So what does that say?
Resistor represents greater fraction of total resistance.
Yeah. Good. Okay. Okay. Good. So that's what we said. Yeah. Yeah. That's fine. Okay. Right. Part B. Yeah. So to protect ammeters from damage, they're often connected with a diode or LED in parallel with them in circuit. Explain how this precaution might protect them. So here you have an ammeter, and here you remember we have an LED. Now I don't know if you remember what's special about LEDs. If you remember their graph, it's like this IV, and they go up here like this. So at the beginning the resistance is big and later it's small. Okay? So just remember, at the beginning it's big and then later it's small. Okay, so imagine here you have a small current. So some of it will go this way and some of it will go this way. And if this is small, then this ore here will be big. Okay? And I want to know, you have, what could you say here? V, I, yeah. So you know V equals I ore. Okay? So the I and the ore have an opposite relationship if the V is constant. If this is constant voltage, it's opposite relationship. So in other words, if this guy here is big, then this one here would be small. And so the current goes this way, which is good because you don't want... Okay, imagine we have our ammeter here and this is 100 milliamps, but 90 milliamps go here and then 10 milliamps go here. What will the ammeter say? It will say 10 milliamps. But is it 10 milliamps? No, it's really 100. So what we want is, we want this to be small and this to be big. However, suppose there's a problem. Suppose you get too much current. Too much current. That will break the ammeter. Yes? Some current goes up here, some current goes up here. If there's too much current, what will happen to the resistance when the current is really big? The resistance will become small. So this will now become a small resistor. But remember that I and ore have an opposite relationship. So it means most of the current will go this way, and only some of the current will go through the ammeter. In other words, if you put an LED here in parallel, it doesn't change the value so much, but it gives protection in case you get too much current. So how can we explain this in words as well? Now, you can explain this in pictures if it's clear, if you have clear pictures like here. But I think I would say the LED will draw more current if there is a sudden surge, because two reasons. Number one, high current means low resistance, and number two, current will be inversely proportional to 1 over resistance. Okay, kind of a lot for 3 marks. Okay, last question, C. Do you understand, guys, what I mean here by draw? So the LED will draw, that means take more current if there's a sudden surge, if you suddenly get too much current. Yeah? Okay. C. Question C is, draw the circuit to measure the EMF and the internal resistance. So I hope you remember this. You have battery. Like this. You have an internal resistance here. This is E, this is R. You have a variable resistor here. You have an ammeter, you can put it here. We'll put our switch here. And we need to put the voltmeter. Now you can put the voltmeter in two places. You can put it here, or you can put it, oh my, you can put it up the top. I think I'll put it up the top. Well, well, well. Isn't that nice?
You can't cycle in.
I'll have to wait. Is this okay? For 3 marks? Do you remember this graph? This circuit?
Oh, only this?
So let's draw the circuit. Okay, that's nice. And then part 2 is they want to explain the graph. So what you could do is you could plot, for example, V against I, and you get a graph like this. Don't worry, I'll protect you. What shape is this graph? Well, if I put the V here and the I here, it actually goes down. And this value here represents the E, and then the R is equal to minus the slope. Yeah, there you go, 5 marks. Right? Oh my goodness.
Oh, no, that small R is the R inside here?
Yeah, there it is there.
Oh.
Yeah? Lastly, finally. Cars have batteries of about 15 volts. Starting a car requires a large power supply to an electric motor. Explain why when starting a car, other items in the car such as the headlights and radio go dim or switch off. So you know when you start your car, maybe the lights go off or the radio goes off. Why is that? Well, the reason is the starter motor requires basically nearly all of the energy provided by the battery. Therefore, leaving not enough energy for everything else.
Was that spell the starter
Motor, sorry.
M-O-R-T?
M-O-T-O-R. The starter motor requires much of the energy provided by the battery, therefore leaving not enough energy for everything else. What did they say in the marking scheme?
Large power requires large current.
Yeah, okay. So, the starter motor requires much of the energy, so that means large power. And then what did you say?
When large current flows, PD is lost through the internal resistance of battery.
Yeah, okay.
So terminal voltage drops, causing items to switch off.
Yep, same thing really.
What's mean max 2?
Don't give the student more than 2, because it's 2 marks.
It's too difficult. I don't think I can answer this kind of question. Worrying.
So the other way of saying it alternatively is, what do they say? The internal resistance consumes all the energy. Anyways, that exam I know had a lot of English in it, and I know you don't like English. And one sec.